Hi, everyone, and thanks for coming today. My name is David Eldred. This is session 513, and we're going to talk about video encoders and decoders today. All right, we want to make sure that no matter what you're doing with video in your application, you have access to hardware encoders and decoders. This will help users, this will improve user experience in a number of ways. Obviously, they'll get better performance, and it will be far more efficient. But most importantly, this will extend battery life. Users will really appreciate it if their OS X, if their portables, as well as their iOS devices have improved battery life. And as an added bonus, people with portables will love it if their fans don't kick in every time they're doing video processing. So today we're going to break this down into a few case studies. We're going to look at some common user scenarios. The first scenario we're going to talk about is the case where you have a stream of H.264 data coming in over the network, and you want to display that inside of a layer in your application. The next one we're going to talk about is the case where you have a stream of H.264 data coming in over the network, but you don't just want to display that in your application, but you want to actually get access to those decoded CV pixel buffers. Next, we'll be talking about the case where you have a sequence of images coming in from the camera or someplace else, and you'd like to compress those directly into a movie file. And accompanying that, there's the case where you have a stream of images coming in from the camera or someplace else, and you'd like to compress those but get direct access to those compressed sample buffers so that you can send them out over the network or do whatever you like with them. And then finally, we're going to give you an intro to our new multipass APIs that we're introducing in iOS 8 and Yosemite. All right, let's do a quick overview of our media interface stack. You've seen stuff like this earlier this week, but we'll do it once more. And there's a little focus on video in my view of this, because we're talking about video. So at the top, we have AV-Kit. AV-Kit provides very easy-to-use, high-level, view-level interfaces for dealing with media. Below that, we have AV Foundation. AV Foundation provides an easy-to-use Objective-C interface for a wide range of media tasks. And below that, we have Video Toolbox. Video Toolbox has been there on OS X for a while, but now it's finally populated with headers on iOS. This provides direct access to encoders and decoders. And below that, we have Core Media and Core Video. These frameworks provide many of the necessary types that you'll see in the interfaces in the rest of the stack. So today we're going to focus on AV Foundation and the Video Toolbox. In AV Foundation, we'll be looking at some interfaces that allow you to decode video directly into a layer in your application or compress frames directly into a file. And the Video Toolbox will be looking at these interfaces to give you more direct access to encoders and decoders. So you can decompress directly to CV pixel buffers or compress directly to CM sample buffers. So a quick note on using these frameworks. A lot of people think they have to dive down to the lowest level and use the Video Toolbox in order to get hardware acceleration. But that's really not true. On iOS, AV-Kit, AV Foundation, and Video Toolbox will all use hardware codecs. On OS X, AV-Kit and AV Foundation will use hardware codecs when they're available on the system and when it's appropriate. And Video Toolbox will use hardware codecs when it's available on the system and when you request it. All right. So before we dive into more stuff, I'm going to do a quick look at this cast of characters. These are some of the common types that you'll encounter in these interfaces. First off, there's CV pixel buffer. CV pixel buffer contains a block of image data. And wrapping that buffer of data is the CV pixel buffer wrapping. And the CV pixel buffer wrapping tells you how to access that data. It's got the dimensions, the width and the height. It's got the pixel format, everything you need in order to correctly interpret the pixel data. Next, we've got the CV pixel buffer pool. The CV pixel buffer pool allows you to efficiently recycle CV pixel buffer backings. Those data buffers can be very expensive to constantly allocate and deallocate. So pixel buffer pool allows you to recycle them. The way a pixel buffer pool works is you allocate a CV pixel buffer from the pool, and the CV pixel buffer is a ref-counted object. When everyone releases that CV pixel buffer, the data backing goes back into the pool, and it's available for reuse next time that you allocate a pixel buffer from that pool. Next thing is pixel buffer attributes. This isn't actually a type like the rest of the things in this list, but it's a common object you'll see listed in our interfaces. You'll see requests for pixel buffer attributes dictionaries. Pixel buffer attributes are a CF dictionary containing a set of requirements for either a CV pixel buffer or a pixel buffer pool. This includes this can include several things. This can include dimensions that you're requesting, the width and the height. This can include a specific pixel format or a list of pixel formats that you'd like to receive. And you can include specific compatibility flags, requesting compatibility with specific display technologies, such as OpenGL, OpenGLES, or Core Animation. All right, next we've got CM time. CM time is the basic description of time that you'll see in our interfaces. This is a rational representation of a time value. It contains a 64-bit time value, that's the numerator, and a 32-bit timescale, which is the denominator. We use this sort of rational representation so that these time values can be passed throughout your media pipeline, and you won't have to do any sort of rounding on them. All right. Next, CM video format description. You'll see this in a bunch of our interfaces, and a CM video format description is basically a description of video data. This contains the dimensions, this includes the pixel format, and there's a set of extensions that go along with the CM video format description. These extensions can include information information used for displaying that video data, such as pixel aspect ratio, and it can include color space information. And in the case of H.264 data, the parameter sets are included in these extensions, and we'll talk about that more a little bit later. All right, next is CM block buffer. CM block buffer is the basic way that we wrap arbitrary blocks of data in core media. In general, when you encounter video data, compressed video data in our pipeline, it will be wrapped in a CM block buffer. All right, now we have CM sample buffer. You'll see CM sample buffers show up a lot in our interfaces. These wrap samples of data. In the case of video, CM sample buffers can wrap either compressed video frames or uncompressed video frames. And CM sample buffers build on several of the types that we've talked about here. They contain a CM time. This is the presentation time for the sample. They contain a CM video format description. This describes the data inside of the CM sample buffer. And finally, in the case of compressed video, they contain a CM block buffer. And the CM block buffer has the compressed video data. And if it's an uncompressed image in the CM sample buffer, the uncompressed image may be in a CV pixel buffer, or it may be in a CM block buffer. All right, next we've got CM clock. CM clock is a core media wrapper around a source of time. And like the clock on a wall, there's no clocks on the wall here, but like a clock on the wall, time is always moving and it's always increasing on a CM clock. One of the common clocks that you'll see used is the host time clock. So if you CM clock get host time clock will return a clock which is based on mock absolute time. So CM clocks are hard to control. You can't really control them. As I mentioned, they're always moving and always at a constant rate. So CM time base provides a more controlled view onto a CM clock. So if we go ahead and create a CM clock a CM time base based on the host time clock, we could then set the time to time 0 on our time base. Now, time 0 on our time base maps to the current time on the CM clock. And you can control the rate of your time base. So if you were then to go and set your time base rate to 1, time will begin advancing on your time base at the same rate at which the clock is advancing. And CM time bases can be created based on CM clocks, or they can be created based on other CM time bases. All right, let's hop into our first use case. This is the case where you have a stream of data coming in over the network. And since it's video data coming over the network, we can safely assume it's a cat video. And so we've got AV sample buffer display layer, which can take a sequence of compressed frames and display it in a layer inside of your application. AV sample buffer display layer shipped in Mavericks, and it's new in iOS 8. So let's take a look inside AV sample buffer display layer. As I mentioned, it takes a sequence of it takes a sequence of compressed frames as input, and these need to be in CM sample buffers. Internally, it's going to have a video decoder, and it will decode the frames into CV pixel buffers, and it will have a sequence of CV pixel buffers queued up, ready to display in your application at the appropriate time. But I mentioned we were getting our data off of the network. A lot of times when you're getting a stream of compressed video off of the network, it's going to be in the form of an elementary stream. And I mentioned that AV sample buffer display layer wants CM sample buffers as its input. Well, there's a little bit of work that has to happen here to convert your elementary stream data into CM sample buffers. So let's talk about this. H.264 defines a couple of ways of packaging, the H.264 spec defines a couple of ways of packaging H.264 data. The first one I'm going to refer to as elementary stream packaging. This is used in elementary streams, transport streams, a lot of things with streams in their name. Next is MPEG-4 packaging. This is used in movie files and MP4 files. And in our interfaces that deal with CM sample buffers, Core Media and AV Foundation exclusively want the data packaged in the MPEG-4 packaging. So let's look closer at an H.264 stream. An H.264 stream consists of a sequence of blocks of data packaged in NAL units. These NAL units can contain several different. So this is the network abstraction layer, and these are network abstraction layer units. These can contain a few different things. First off, they can contain sample data. So you could have a single frame of video could be packaged in one NAL unit, or a frame of video could be spread across several NAL units. The other thing that NAL units can contain is parameter sets. The parameter sets, the sequence parameter set and picture parameter set, are chunks of data which the decoder holds onto, and these apply to all subsequent frames. Well, until a new parameter set arrives. So let's look at elementary stream packaging. In elementary stream packaging, the parameter sets are included in NAL units right inside the stream. This is great if you're doing sequential playback. You read in your parameter sets, and they apply to all subsequent frames until new parameter sets arrive. MPEG-4 packaging has the NAL units pulled out, and it's in a separate block of data. And this block of data is stored in the CM video format description. So as I mentioned, each CM sample buffer references this CM video format description. That means each frame of data has access to the parameter sets. This sort of packaging is superior for random access in a file. It allows you to jump anywhere and begin decoding at an iframe. So what do you have to do if you have an elementary stream coming in? Well, you've got your parameter sets in NAL units, and you're going to have to package those in a CM video format description. Well, we provide a handy utility that does this for you. CM video format description create from H.264 parameter sets. All right. So the next difference that we're going to talk about between an elementary stream and MPEG-4 packaging is in the NAL unit headers. So each NAL unit in an elementary stream will have a 3 or 4 byte start code as the header. And in MPEG-4 packaging, we have a length code. So for each NAL unit in your stream, you have to strip off that start code and replace it with a length code. That's the length of the NAL unit. It's not that hard. So let's talk about building a CM sample buffer from your elementary stream. First thing you're going to have to do is take your NAL unit, or NAL units, and replace the start code with the length code. And you'll wrap that NAL unit in a CM block buffer. one note here. For simplicity, I'm showing a single NAL unit, but if you have a frame that consists of several NAL units, you need to include all of the NAL units in your CM sample buffer. So you have a CM block buffer. You have your CM video format description that you created from your parameter sets, and throw in a CM time value. That's the presentation time of your frame, and you have everything you need in order to create a CM sample buffer using CM sample buffer create. All right, let's talk about AV sample buffer display layer and time. So as we saw, all CM sample buffers have an associated presentation timestamp. And our video decoder is going to be spitting out CV pixel buffers, each with an associated presentation timestamp. Well, how does it know when to display these frames? By default, it will be driven off of the host time clock. Well, that can be a little bit hard to manage. The host time clock isn't really under your control. So we allow you to replace the host time clock with your own time base. To do this, you set the time, in the example here, we're creating a time base based on the host time clock, and we're setting that as the control time base on our AV sample buffer display layer. Here, we're setting the time base time to 5, which would mean our frame whose timestamp is 5 will be displayed in our layer. And then we go ahead and set the time base rate to 1. And now our time base begins moving at the same rate as the host time clock, and subsequent frames will be displayed at the appropriate time. All right. So providing the CM sample buffers, the AV sample buffer display layer, there's really two major scenarios that can describe this. First off, there's the periodic source. This is the case where you're getting frames in at basically the same rate at which they're being displayed in the AV sample buffer display layer. This would be the case for a live streaming app, or a live streaming app with low latency, or a video conferencing scenario. The next case is the unconstrained source. This is the case where you have a large set of CM sample buffers at your disposal, ready to feed into the AV sample buffer display layer at one time. This would be the case if you have a large cache of buffered network data, or if you're reading the CM sample buffers from a file. All right, let's talk about the first case. This is really simple. Frames are coming in at the same rate at which they're being displayed. You can go ahead and just enqueue the sample buffers with your AV sample buffer display layer as they arrive. You use the enqueue sample buffer call. All right, the unconstrained source is a little bit more complicated. You don't want to just shove all of those CM sample buffers into the AV sample buffer display layer at once. No one will be happy with that. What you want to do, the AV sample buffer display layer can tell you when its internal buffers are low and it needs more data, and you can ask it when it has enough data. The way you do this is using the request media data when ready on queue. You provide a block in this interface, and AV sample buffer display layer will call your block every time its internal queues are low and it needs more data. Inside of that block, you can go ahead and loop while you're asking whether it has enough data. You use the isReadyForMoreMediaData call. If it returns true, that means it wants more sample buffers. So you keep on feeding sample buffers in. As soon as it returns false, that means it has enough, and you can stop. So it's a pretty simple loop to write. All right. Let's do a quick summary of what we talked about with AV sample buffer display layer. At this point, you should be able to create an AV sample buffer display layer. You've learned how to convert your elementary stream H.264 data into CM sample buffers that will happily be decompressed by your AV sample buffer display layer. We've talked about a couple of scenarios about how you would provide these CM sample buffers to your layer, AV sample buffer display layer. And finally, we talked about using a custom CM time base with the AV sample buffer display layer. All right, so let's dive into our second case. This is the case where you have a stream of H.264 data coming in over the network, but you don't want to just display it in your application. You want to actually decode those frames and get the decompressed pixel buffers. So what we had in AV sample buffer display layer contains a lot of the pieces we need. But instead of accessing the video decoder through the AV sample buffer display layer, we'll access it through the VT decompression session. Like the AV sample buffer display layer, VT decompression session wants CM sample buffers as its input. And it will decode these CM sample buffers to CV pixel buffers and receive those in the output callback that you implement. So in order to create a VT decompression session, you'll need a few things. First, you need to provide a description of the source buffers that you'll be decompressing. This is a CM video format description. If you're decompressing from an elementary stream, you've created this from your parameter sets. If you just have a CM sample buffer that you want to decompress, you can pull it straight off the CM sample buffer. Next, you need to describe your requirements for your output pixel buffers. Use a pixel buffer attributes dictionary for this. And finally, you need to implement a VT decompression output callback. All right, let's talk about describing your requirements for the output pixel buffers. Here you need to create a pixel buffer attributes dictionary. So let's look at a scenario where we want to use the output CV pixel buffers in an OpenGLES render pipeline. Really, the only requirement here that we have for our output pixel buffers is that they be OpenGLES compatible. So we can go ahead and just create a CF dictionary or NS dictionary specifying the KCV pixel buffer OpenGLES compatibility key and set it to true. So it can be very tempting to, when you're creating these pixel buffer attributes dictionaries, to be very specific. That way, there's no surprises about what you get out of the VT decompression session. But there's some pitfalls here. So let's look at this case where we had KCV pixel buffer OpenGLES compatibility key set to true. Here, our decompression session, the decoder inside of our decompression session is going to be decoding the frames and outputting YUV CV pixel buffers. In the VT decompression session, we'll then ask, it'll ask itself, is this pixel buffer compatible with those requested attributes? And the answer is yes, that YUV frame is OpenGLES compatible. So it can return that directly to your callback. But let's say you were possessed to add BGRA request to your pixel buffer attributes. So just like before, the decoder inside of our VT decompression session will decode to a YUV format, and we'll ask whether this CV pixel buffer is compatible with the requested output requirements. And it is OpenGLES compatible, but it's certainly not BGRA. So it will need to do an extra buffer copy to convert that YUV data to BGRA data. So extra buffer copies are bad. They decrease efficiency, and they can lead to decreased battery life. So the moral of the story here is don't overspecify. All right, let's talk about your output callback. So the output callback is where you'll receive the decoded CV pixel buffers. And CV pixel buffers don't have a built-in timestamp, so you'll receive the presentation timestamp for that pixel buffer here. And if there are errors or the frame is dropped for any reason, you'll receive that information in the output callback. And it's important to note that the output callback will be called for every single frame that you push into the VT decompression session, even if there's an error, even if it's dropped. All right, let's talk about providing frames to your VT decompression session. To do that, you call VT decompression session decode frame. Just like AV sample buffer display layer, you need to provide these as CM sample buffers. And you need to provide these frames in decode order. And by default, VT decompression session decode frame will operate synchronously. This means that your output callback will be called before VT decompression session decode frame returns. If you want asynchronous operation, you can pass in the flag requesting enable asynchronous decompression. All right, let's talk about asynchronous decompression then. With asynchronous decompression, the call to VT decompression session decode frame returns as soon as it hands the frame off to the decoder. But decoders often have limited pipelines for decoding frames. So when the decoder's internal pipeline is full, the call to VT decompression session decode frame will block until space opens up in the decoder's pipeline. We call this decoder back pressure. So What this means is that even though you're calling VT decompression session decode frame and requesting asynchronous decompression, we will be doing the decompression asynchronously, but the call can still block in some cases. So be aware of that. You're doing asynchronous decompression, but the call can block, so don't perform UI tasks on that thread. All right. If you find yourself in a situation where you want to ensure that all asynchronous frames have been cleared out of the decoder, you can call VT decompression session and wait for asynchronous frames. This call will not return until all frames have been emitted from the decompression session. So sometimes while decoding a sequence of video frames, there will be a change in the CM video format description. So let's look at the case where we had a sequence of an elementary stream, and we created the first format description out of the first parameter sets that we encountered. So now we have format description 1 with our first SPS and PPS. We can go ahead and create our VT decompression session with that format description and decode all the subsequent frames with that format description attached to the CM sample buffer until we encounter a new SPS and PPS in the stream. Then we need to create a new format description with the new SPS and PPS, and we have to make sure that the decompression session can switch between these format descriptions. So to do that, you call VT decompression session can accept format description. This will ask the decoder whether it's able to transition from format description 1 to format description 2. If the answer is true, yes, it can handle accept the new format description. That means you can pass subsequent samples with that new format description attached to them into the decompression session, and everything will work fine. If it returns false, that means the decompressor cannot transition from that first format description to the second format description. And you'll need to create a new VT decompression session and be sure to pass the new frames into that one. And be sure to release that old VT decompression session when you're no longer using it. All right. Quick summary of what we talked about with VT decompression session. We talked about creating the VT decompression session and how to make optimal decisions when creating your pixel buffer attributes dictionary for specifying your output requirements. We talked about running your decompression session both synchronously and asynchronously, and we talked about handling changes in the CM video format description. So with that, let's hop into case 3. This is the case where you have a stream of CV pixel buffers or frames coming in from a camera or another source, and you want to compress those directly into a movie file. Well, for this, and you may be familiar with this already, we have AV Asset Writer. AV Asset Writer has an encoder internally, and it's going to be encoding those frames into CM sample buffers. And it's got some file writing smarts, so it can write these optimally into a movie file. We're not actually going to talk more at this point about AV Asset Writer, but it's an important concept, an important thing to bring up in the context of this talk. So if you want more information on the AV Asset Writer, you can go back to WWDC 2013 and the talk Moving to AV Kit and AV Foundation, or 2011, Working with Media and AV Foundation. All right, let's just hop straight into case 4. This is the case where you have that stream of data coming in from your camera, and you want to compress it, but you don't want to write it into a movie file. You want direct access to those compressed sample buffers. So we want to approach our video encoder through a VT compression session rather than through the AV Asset Writer. So just like the AV Asset Writer, VT compression session takes CV pixel buffers as its input, and it's going to compress those and return CM sample buffers. And we can go ahead and send that compressed data out over the network. So to create a VT compression session, you'll need a few things. And this is really simple. You just need to specify the dimensions you want for your compressed output. You need to tell us what format you want to compress to, such as KCM video codec type H.264. And you can optionally provide a set of pixel buffer attributes describing your source CV pixel buffers that you'll be sending to the VT compression session. And finally, you need to implement a VT compression output callback. So you've created a VT compression session. Now you want to configure it. You configure a VT compression session using VT session set property. In fact, you can have a whole sequence of VT session set property calls. So I'm going to go through a few common properties here, but this is not an exhaustive list. The first one I'm going to mention is allow frame reordering. By default, the H.264 encoder will allow frames to be reordered. That means the presentation timestamp that you pass them in will not necessarily equal the decode order in which they're emitted. If you want to disable this behavior, you could pass false to allow frame reordering. The next one, average bit rate. This is how you set a target bit rate for the compressor. H.264 entropy mode. Using this, you can specify CAVLC compression or KBAC compression for your H.264 encoder. All right, and then there's the real-time property. The real-time property allows you to tell the encoder that this is a real-time encoding operation, such as in a live streaming case, conferencing case, as opposed to more of a background activity, like a transcode operation. And the final one I'm going to mention here is the profile level key. This allows you to specify specific profiles and levels, or specific profiles and allow us to choose the correct level. And this is definitely not an exhaustive list. There's a lot of these options available. So go ahead and look in vtcompressionproperties.h and see what we have for you. All right, let's talk about providing CV pixel buffers to your VT compression session. Use VT compression session encode frame to do this. And you'll need to provide CV pixel buffers. And as I've mentioned, CV pixel buffers don't have a presentation timestamp built into them. So as a separate parameter, you'll provide the presentation timestamp. You need to feed the frames in presentation order. And it's one more note about the presentation order. The presentation timestamps must be increasing. No duplicate presentation timestamps, no timestamps that go backwards. And so compression sessions, compression operations usually require a window of frames that they'll operate on. So your output may be delayed. So you may not receive a compressed frame in your output callback until a certain number of frames have been pushed into the encoder. All right, and finally, if you reach the end of the frames that you're passing to the compression session and you want to have it emit all of the frames that it's received so far, you can use VT compression session complete frames. All pending frames will be emitted. All right, let's talk about your output callback. So your output callback is where you'll receive your output CM sample buffers. These contain the compressed frames. If there were any errors or dropped frames, you'll receive that information here. And final thing, frames will be emitted in decode order. So you provided frames to the VT compression session in presentation order, and they'll be emitted in decode order. All right. Well, so you've compressed a bunch of frames. They're now compressed in CM sample buffers, which means that they're using MPEG-4 packaging. And you want to send that out over the network, which means you may need to switch these over to elementary stream packaging. Well, once again, you're going to have to do a little bit of work. So we talked about the parameter sets before. So the parameter sets will, in your MPEG-4 packaged H.264, will be in the CM video format description. So the first thing you're going to have to do is extract those parameter sets and package them as NAL units to send out over the network. Well, we provide a handy utility for that too. CM video format description, get H.264 parameter set at index. All right, and the next thing that you need to do is the opposite of what we did with the AV sample buffer display layer. Our NAL units are all going to have length headers, and you're going to need to convert those length headers into start codes. So as you extract each NAL unit from the compressed data inside the CM sample buffer, convert those headers on the NAL units. All right, a quick summary about what we talked about with the VT compression session. We talked about creating the VT compression session, and we've talked about how to configure it using the VT session set property call. And we talked about how you would provide CV pixel buffers to the compression session. And finally, we talked about converting those CM sample buffers into an H.264 elementary stream packaging. All right, and with that, I'd like to hand things off to Eric so he can talk about multipass.
Good morning, everyone. My name is Eric Turnquist. I'm a core media engineer, and today I want to talk to you about multipass encoding. So as a media engineer, we often deal with two opposing forces, quality versus bitrate. So quality is how pristine the image is, and we all know and we've seen great quality video, and we really don't like seeing bad quality video. Bitrate is how much data per time is in the output media file. So let's say we're preparing some content. If you're like me, you go for high quality first. So great, we have high quality. Now in this case, what happens with the bitrate? Well, unfortunately, if you have high quality, you also tend to have a high bitrate. Now that's okay, but not what we want if we're streaming this content or storing it on a server. So in that case, we want a low bitrate, but the quality isn't going to stay this high. Unfortunately, that's also going to go down as well. So we've all seen this as blocky encoder artifacts or an output image that doesn't really even look like the source. We don't want this either. Ideally, we want something like this, high quality and low bitrate. In order to achieve that goal, we've added multipass encoding to AV Foundation and Video Toolbox. Yeah. So first off, what is multipass encoding? Well, let's do a review of what single pass encoding is first. So this is what David covered in his portion of the talk. With single pass encoding, you have frames coming in, going into the encoder, and being emitted. In this case, we're going to a movie file. Then once you're done appending all the samples, we're finished, and we're left with our output movie file. Simple enough. Let's see how multipass differs. So you have uncompressed frames coming in, going into the compression session, being emitted as compressed samples. Now we're going to change things up a little bit. So we're going to have our frame database. This will store the compressed samples and allow us random access and replacement, which is important for multipass. And we're going to have our encoder database. This will store frame analysis. So we're done appending for one pass, and the encoder will decide, I think I can actually do better in another pass. So I can tweak the parameters a little bit to get better quality. It will request some samples, and you'll go through and send those samples again to the encoder. And then it may decide, I'm done, or I want more passes. In this case, let's assume that we're finished. So we no longer need the encoder database or the compression session, but we're left with this frame database, and we want a movie file. So we need one more step. There's a final copy from the frame database to the output movie file. And then that's it. We have a multipass encoded video track on a movie file. Cool. Let's go over some encoder features. So my first point, as I want to make a note of, is that David said that single pass is hardware accelerated, and multipass is also hardware accelerated. So you're not losing any hardware acceleration there. Second point is that multipass has knowledge of the future. Now, it's not some crazy time-traveling video encoder. Bonus points, whoever files that enhancement request. It allows, or is able to see your entire content. So in single pass, as frames come in, the encoder has to make assumptions about what might come next. In multipass, it's already seen all your content, so it can make much better decisions there. Third, it can change decisions that it's made. So in single pass, as soon as a frame is emitted, that's it. It can no longer change. It can no longer change its mind about what it's emitted. In multipass, because the frame database supports replacement, each pass it can go through and change its mind about how to achieve optimal quality. And as a result of this, you really get optimal quality per bit. So it's sort of like having a very awesome custom encoder for your content. So that's how multipass works and some features. Let's talk about new APIs. So first off, let's talk about AV Foundation. In AV Foundation, we have a new AV Asset Export Session property. We have new pass descriptions for AV Asset Writer input. And we have reuse on AV asset reader output. So first, let's go over an overview of AV asset export session. In AV asset export session, you're going from a source file, decoding them, then performing some operation on those uncompressed buffers, something like scaling or color conversion. Then you're encoding them and writing them to a movie file. So in this case, what does AV asset export session provide? Well, it does all this for you. It's the easiest way to transcode media on iOS and OS X. So let's see what we've added here. So in AV asset export session, multiple passes are taken care of for you automatically. There's no work that you have to do to send the samples between passes. And also, it falls back to single pass if multipass isn't supported. So if you choose a preset that uses a codec where multipass isn't supported, don't worry, it will use single pass. And we have one new property, set this to yes, and you're automatically opted into multipass, and that's it. So for a large majority of you, this is all you need. Next, let's talk about AV Asset Writer. So AV Asset Writer, you're coming from uncompressed samples, you want to compress them and write them to a movie file. You might be coming from an OpenGL or OpenGLES context. In this case, what does AV Asset Writer provide? Well, it wraps this portion, going from the encoder to the output movie file. Another use case, it's similar to AV Asset Export Session, where you're going from a source movie file to a destination output movie file and modifying the buffers in some way. Well, in this case, you're going to use an AV Asset Reader output and an AV Asset Writer input. You're responsible for sending samples from one to the other. Let's go over new AV Asset Writer input APIs. So like AV Asset Export Session, you need to enable multipass. So set this to yes, and you're automatically opted in. Then after you're done appending samples, you need to mark the current pass as finished. So what does this do? Well, this triggers the encoder analysis. The encoder needs to decide if I need to perform multiple passes, and if so, what time ranges. So the encoder might say, I want to see the entire sequence again, or I want to see subsets of the sequence. So how does the encoder talk about what time ranges it wants for the next pass? Well, that's through an AV Asset Writer input pass description. So in this case, we have time from 0 to 3, but not the sample at time 3, and samples from 5 to 7, but not the sample at time 7. So a pass description is the encoder's request for media in the next pass, and it may contain the entire sequence or subsets of the sequence. On a pass description, you can query the time ranges that the encoder has requested by calling source time ranges. All right, let's talk about how AV Asset Writer input uses pass descriptions. So when you trigger the encoder analysis, the encoder needs to reply with what decisions it's made. So you provide a block on this method to allow the encoder to give you that answer. So this block is called when the encoder makes a decision about the next pass. In that block, you can get the new pass description, the encoder's decision about what content it wants for the next pass. Let's see how that works all in a sample. So here's our sample. We have our block callback that you provide. Inside that callback, you call current pass description. This asks the encoder what time ranges it wants for the next pass. If the pass is non-nil, meaning the encoder wants data for another pass, you reconfigure your source. So this is where the source will send samples to the AV Asset Writer input. And then you prepare the AV Asset Writer input for the next pass. You're already familiar with request media data when ready on queue. If the pass is nil, that means the encoder has finished passes, then you're done. You can mark your input as finished. All right, let's say you're going from a source media file. That was in our second example. So we have new APIs for AV Asset Reader output. You can prepare your source for multipass by saying supports random access equals yes. Then when the encoder wants new time ranges, you need to reconfigure your AV Asset Reader output to deliver those time ranges. So that's reset for reading time ranges with an NS array of time ranges. Finally, when all passes have completed, you call mark configuration as final. This allows the AV Asset Reader output to transition to its completed state so it can start tearing itself down. All right, now there's a couple shortcuts you can use if you're using AV Asset Reader and AV Asset Writer in combination together. So you can enable an AV Asset Reader output if the AV Asset Writer input supports multipass. So if the encoder supports multipass, we need to support random access on the source. Then you can reconfigure your source to deliver samples for the AV asset writer input. So with your reader output, call reset for reading time ranges with the pass descriptions time ranges. Let's go over that in the sample. So instead of delivering for an arbitrary source, we now want to deliver for our AV asset reader output. So we call reset for reading time ranges with the pass description source time ranges. Great, so that's the new API in AV Foundation for multipass. Let's talk next about Video Toolbox. So with Video Toolbox, our encoder frame analysis database, we like to call this our VT multipass storage. We also have additions to VT compression session, which David introduced in his portion of the talk, and the compressed frame database, or as we call it, the VT frame silo. So let's go over the architecture, but this time replacing the frame database and the encoder database with the objects that we actually use. So in this case, we have our VT frame silo and our VT multipass storage. We're done with this pass. The encoder wants to see samples again. We're sending in those samples that it requests. Then we're finished, and we can tear down the VT multipass storage in the compression session. And we're left with our frame silo. So this is where we need to perform the copy from the frame silo to the output movie file. Great, we have our output movie file. So first off, let's go over what the VT multipass storage is. So this is the encoder analysis. This is a pretty simple API. First, you create the storage, and then you close the file once you're finished. So that's all the API that you need to use. The data that's stored in this is private to the encoder, and you don't have to worry about it. Next, let's talk about additions to VT compression session. So first, you need to tell the VT compression session and the encoder about your VT multipass storage. So you can do that by setting a property. This will tell the encoder to use multipass and use this VT multipass storage for its frame analysis. Next, we've added a couple functions for multipass. So you call begin pass before you've appended any frames. Then after you're done appending frames for that pass, you call end pass. End pass also asks the encoder if another pass can be performed. So if the encoder wants another pass to be performed, you need to ask it what time ranges of samples it wants for the next pass. That's called via VT compression session get time ranges for next pass, and you're given a count and a C array of time ranges. Now let's talk about the VT frame silo. So this is the compressed frame store. So like the other objects, you create it, and then you want to add samples to this VT frame silo. So frames will automatically be replaced if they have the same presentation timestamp, and how this data is stored is abstracted away from you, and you don't need to worry about it. It's a convenient database for you to use. Then you can prepare the VT frame silo for the next pass. This optimizes the storage for the next pass. Finally, let's talk about the copy from the VT frame silo to the output movie file. So you can retrieve samples for a given time range. This allows you to get a sample in a block callback that you provide and add it to your output movie file. Right? That's the new Video Toolbox APIs. So I want to close with a couple considerations. So we've talked about how multipass works and what APIs you can use in AV Foundation and Video Toolbox, but we need to talk about your use cases and your priority in your app. So if you're performing real-time encoding, you should be using single pass. Real-time encoding has very specific deadlines of how much compression can take, and multipass will perform more passes over the time range. So use single pass in these cases. If you're concerned about using the minimum amount of power during encoding, use single pass. Multiple passes will take more power, and as will the encoder analysis. If you're concerned with using the minimum amount of temporary storage during the encode or transcode operation, use single pass. The encoder analysis storage and the frame database will use more storage than the output media file. However, if you're concerned about having the best quality for your content, multipass is a great option. If you want to be as close to the target bitrate you set on the VT compression session or asset writer as possible, use multipass. Multipass can see all of the portions of your source media, and so it can allocate bits only where it needs to. It's very smart in this sense. If it's okay to take longer in your app, so if it's okay for the encoder transcode operation to take longer for better quality, multipass is a good option. But the biggest takeaway is that in your app, you need to experiment. So you need to think about your use cases and your users and if they're willing to wait longer for better quality. Next, let's talk about content. So if your app has low quality or low complexity content, think of this like a title sequence or a static image sequence. Well, single pass and multipass are going to both give you great quality here, but multipass won't give you much better quality than single pass. These are both pretty easy to encode. Next, let's talk about high complexity content. So think of this as classic encoder stress tests. Water, fire, explosions. We all love to do this. But single pass and multipass are both going to do well, but multipass probably won't do much better than single pass. This kind of content is hard for encoders to encode. Where is multipass a better decision? Well, that's in varying complexity. So think of this as a feature-length movie or a documentary in Final Cut Pro or an iMovie trailer. You might have low complexity regions, a title sequence, high complexity transitions. Because there's a lot of different kinds of content, multipass is able to analyze those sections and really give you the best quality per bit. But again, the message is with your content, you need to experiment. So you know your content, and you should know if multipass will give you a good benefit in these cases. So let's go over what we've talked about today. AV Foundation provides powerful APIs to operate on media, and for most of you, these are the APIs you will be using. Now, when you need the extra power, Video Toolbox APIs provide you direct media access. If you fall into one of the use cases that David talked about, this is a good way to use Video Toolbox. Finally, multipass can provide substantial quality improvements, but you need to think about your app, your use cases, and your users before you enable it. So for more information, here's our evangelism email. We have AV Foundation documentation and a programming guide, and we can answer your questions on the developer forums. For those of you that are watching online, a lot of these talks have already happened if you're here live, so these are the talks you might be interested in. Thanks, everyone, and have a good rest of your day.